For 75 years, humanity has been listening to the cosmos with increasingly sensitive instruments. Project Ozma began in April of 1960, when Frank Drake pointed an 85-foot radio dish at the star Tau Ceti and waited for a signal. Since then, we have built the Allen Telescope Array, the Very Large Array, the Meerkat in South Africa, the 500-metre Aperture Spherical Telescope in China. We have invested a billionaire's $100 million fortune in the Breakthrough Listen program. We have harnessed the spare computing cycles of 5 million volunteer machines through SETI at home. We have scanned tens of thousands of nearby stars at every plausible frequency. The cumulative result of all of it, after 65 years, is one single 72-second moment in 1977 that has never repeated, and an otherwise perfect, unbroken silence. The silence is not a failure of our instruments. The silence is the measurement. So what does it mean? Make yourself comfortable. Subscribe so you can join the next journey, and stick around, because what we are about to walk through is the menu of possible answers, and every single one of them is terrifying. Let's dive in. Part 1. The lunch that started it all. In the summer of 1950, 4 physicists sat down to lunch at the Fuller Lodge at Los Alamos National Laboratory. The lodge sat at the edge of a mesa in northern New Mexico, 2,300 meters above sea level, in a town that less than a decade earlier had not existed at all. The cottonwoods outside the lodge windows were old enough to remember the wartime construction. The men at the table were not. They had been brought here by physics, by the war, and by the project that had ended it. There was Enrico Fermi, the Italian-born Nobel laureate visiting from Chicago. There was Edward Teller, the Hungarian theoretician who would, within 2 years, become the principal architect of the hydrogen bomb. There was Emil Konopinski, who had worked on the same theoretical chain at Los Alamos. And there was Herbert York, a young experimentalist who, decades later, would write the letter that preserved what happened next for the historical record. The conversation that day drifted in the way physicists' conversations drift. It started with a cartoon. The previous week's New Yorker had published a piece showing a group of aliens climbing out of a flying saucer, carrying off public trash cans. The cartoon was meant as a joke about the recent wave of UFO sightings that had washed across the United States. The physicists laughed about it. They moved on. Fermi began estimating. This was his trademark. Given any quantity in the world, Fermi could derive an order of magnitude answer to a question about it within minutes, often without any preparation at all. He was the founder of what would later be called the Fermi problem. Questions like how many piano tuners live in Chicago, how many leaves are on the tree in your yard, how much energy does the human race consume in an hour? The answers came from stacking small reasonable assumptions on top of one another until something useful fell out the other end. Fermi would do this on napkins. He would do this at lunch. He would, when asked at Trinity in 1945 whether the bomb was about to detonate correctly, drop torn paper from his hand to estimate the yield from the displacement caused by the blast wave. He was, in every direction, the same kind of mind. He took quantities and turned them into answers. That afternoon, somewhere between the soup and the coffee, Fermi looked up. He had been thinking, by his own later account, about the size of the galaxy. He had been thinking about the age of the universe. He had been thinking about how many stars were out there, how many of them likely had planets, how many of those planets might be reasonable places for the chemistry of life to start, how long it took for life to become intelligent, how long an intelligent civilization might persist once it had emerged, and how fast such a civilization might be capable of moving between stars. He had run the calculation in his head. The numbers came out wrong. He turned to the men at the table. Teller would later recall the moment slightly differently from Konopinski, and Konopinski would recall it slightly differently from York. None of them wrote down the exact words at the time. None of them could agree, decades later, what the precise phrasing had been. They agreed only that Fermi asked, in 3 words or 4 or 6, a question that they all understood instantly to mean the same thing. Where is everybody? 3 words. A question dropped into a New Mexico afternoon by accident between bites of lunch. A question whose answer should have been simple. There are many other star systems, many other planets, many other places where life might exist, and somewhere among them certainly must be the kind of intelligent civilization that builds machines, transmits signals, and explores. The galaxy is enormous. The math is straightforward. The conclusion should have written itself. But the conclusion did not write itself. Fermi had done the arithmetic, and the arithmetic had broken. Somewhere in the chain of reasonable assumptions, something was wrong. Either his numbers were wrong, or the universe was much stranger than the numbers said. There should have been visitors by now. There should have been signals. There should have been ships, probes, evidence, anything. The galaxy was old enough, big enough, and crowded enough with possibility that it should have been busy. And yet, when the 4 men at the table looked up at the New Mexico sky later that evening, the sky was empty. No visitors, no signals, just the quiet light of stars that, if Fermi's reasoning was correct, should have been speaking to one another for billions of years. That single sentence, 3 words long, has since become the founding sentence of one of the most disturbing fields in modern science. It is the seed from which has grown the search for extraterrestrial intelligence, the Drake equation, the Great Filter, the Dark Forest, the Zoo hypothesis, the Berserker hypothesis, the estivation hypothesis, the rare earth hypothesis, and a small library of philosophical work that asks not whether we are alone, but what would have to be true about the universe for us to be alone. Every space mission with an astrobiology component now traces its lineage back to that lunch. Every radio survey, every exoplanet atmospheric study, every paper on the long-term survival prospects of technological civilizations, all of it, in the end, is the descendants of that question. And now, more than 75 years later, we still do not have an answer. What we have instead is a menu of possible answers. Each of them has been worked out in detail by serious scientists, by mathematicians, by philosophers, by economists, by science fiction novelists, whose ideas have been promoted into the peer-reviewed literature. Each of them is internally consistent. Each of them is, taken on its own, terrifying. This is what we're going to walk through, layer by layer, in this video. 10 of them. 10 reasons the Fermi paradox might be the universe's scariest truth. 10 ways of looking at the same silence, each one removing a comfort that the previous one had offered. We will count down from layer 10 to layer 1. We will end where the chain of reasoning ends, with the question that the silence itself is asking us, and with the realization that, regardless of which answer turns out to be the right one, the answer was never going to be a comfortable one. This is a long story. The pacing will be slow. There is no urgency in it. The question has been with us for 75 years, and it will be with us for many more. So let yourself settle into it. Let the layers stack the way they need to. By the time we get to layer 1, you will have a different relationship with the night sky than you had when this video started. Whether that is a better relationship is something only you will be able to decide. We are going to begin, as Fermi did, with the math. Part 2. The mathematical nightmare of the Drake equation. In November of 1961, a young astronomer named Frank Drake was tasked with organizing the first formal scientific meeting on the question of extraterrestrial intelligence. The meeting was to be held at the Greenbank Observatory in West Virginia, deep in the Allegheny Mountains, in a radio-quiet zone that the National Radio Astronomy Observatory had carved out of the surrounding hills. 10 people were invited. A dozen would actually attend. The meeting needed an agenda. Drake sat down in his office at the observatory the night before the meeting was to begin. He thought about what the assembled physicists and astronomers would need to discuss. He realized that, in order to even ask whether intelligent civilizations existed elsewhere in the galaxy, you had to first agree on what such a question depended on. You had to enumerate the variables. You had to count the unknowns. He picked up a piece of chalk. He walked to the blackboard, and he wrote down what is now known as the Drake equation. The equation looks like this. The number of communicating civilizations in the Milky Way at any given moment, which Drake called n, is equal to the rate at which stars form in the galaxy, multiplied by the fraction of those stars that have planets, multiplied by the average number of planets per star capable of supporting life, multiplied by the fraction of those planets where life actually emerges, multiplied by the fraction of life-bearing planets on which intelligence eventually develops, multiplied by the fraction of intelligent species that develop a technology capable of broadcasting signals into space, multiplied by the average length of time in years that such a civilization continues to broadcast before going silent. 7 variables, 7 steps. Multiply them together and you get a single number. How many civilizations in the galaxy are, right now, in the process of being detectable? Drake did not write the equation as a prediction. He wrote it as an organizing principle. The point was not to give an answer. The point was to enumerate the things that, in order to give an answer, you would first have to know. It was a confession in mathematical form. It said, here are the things we do not know. Here is how our ignorance breaks down. Here is the structure of the question. The conversation that followed at Greenbank took, at most, a few hours. The participants put numbers on each of the 7 variables, multiplied them together, and came out with a number for n that ranged, depending on whose estimates you believed, from about 1,000 to about 100 million. A galaxy that contained at least 1,000 active broadcasting civilizations. A galaxy that might contain 100 million. The first 3 variables in those days were guesses: the rate of star formation in the galaxy, the fraction of stars that have planets, the average number of habitable planets per star. In the 1960s, astronomers had no exoplanet detections at all, not one. They suspected on theoretical grounds that other stars probably had planets, but they had no way to confirm it. They had no idea what the typical planet count per star might be. They had no idea whether Earth-like worlds were common or were once in a galaxy events. That changed in October of 1995. 2 Swiss astronomers, Michel Mayer and Didier Queloz, working at the Geneva Observatory, announced that they had detected the first confirmed exoplanet orbiting a Sun-like star. The planet was called 51 Pegasi b. It was a gas giant about half the mass of Jupiter, orbiting its star at a distance closer than Mercury orbits the Sun. It was strange. It did not match what astronomers had expected planetary systems to look like. But it was a planet, and it was around a star that was not our Sun, and the announcement broke open a question that had been closed for centuries. In 2009, NASA launched the Kepler Space Telescope. Kepler was a spacecraft with a single purpose. It would stare continuously for 4 years at a patch of sky about the size of your fist held at arm's length, located in the constellations Cygnus and Lyra. It would monitor the brightness of about 150,000 stars in that patch, and it would watch for transits, the tiny periodic dimming that occurs when a planet passes in front of its star from our point of view. By the time Kepler's primary mission ended, it had found thousands of confirmed exoplanets and tens of thousands of candidates. Statistical analysis of the Kepler data, published by Steve Bryson and colleagues in the Astronomical Journal in 2021, produced a number that should have stopped people in their tracks. The Milky Way galaxy, the team estimated, contains roughly 6 billion Earth-sized planets in the habitable zones of Sun-like stars alone. Other studies that include the planets of red dwarf stars push that estimate into the tens of billions. The cosmos is not a desert. It is a real estate market with billions of vacancies. Now think about what that means for the Drake equation. The first 3 variables, star formation rate, fraction with planets, fraction in habitable zones, have all come in larger than the founders of the field expected. Virtually every star has at least 1 planet. A meaningful fraction of those planets are roughly Earth-sized and roughly the right temperature for liquid water. Across the Milky Way as a whole, there are now believed to be between 100 billion and 400 billion stars in total. The lowest plausible estimate gives you tens of billions of potentially habitable worlds. The highest gives you well over 100 billion. So if you take the first three variables in the Drake equation and set them to the values modern astronomy now insists on, even a deeply pessimistic estimate of the remaining variables, the probability that life emerges, the probability that life becomes intelligent, the probability that intelligence produces a broadcasting technology, the average duration of such a broadcast, even pessimistic values give you a number for n that is greater than 1. The math insists. Even when you crank the dial in the direction of almost no civilizations ever exist, the math still gives you a galaxy in which we should not be alone. This is the part that catches people off guard. The Drake equation has the reputation of being soft because its later variables are unknown. But this is the wrong way to read it. The right way to read it is to notice what happens when you stack the things we do know on top of the things we do not. The things we do know, the number of stars, the number of planets, the number of Earth-sized worlds in habitable zones, are enormous. To get n down to a number consistent with humanity being the only broadcasting civilization in the entire Milky Way, the unknown variables have to be very, very small. Not unknown small, punishingly small, smaller than a back-of-the-envelope calculation has any right to be. And here is where the discomfort starts. If you sit down with the equation and try to find values for the unknown variables that produce n equal to 1, that is, exactly one broadcasting civilization in the Milky Way, namely us, you find that you have to assume one of two things. Either life is staggeringly rare, or life is common but intelligent broadcasting civilizations vanish staggeringly quickly. There is no easy middle ground. The math will not let you have a middle ground. Either life almost never starts, or it almost never lasts. Either Earth is the first place that life ever happened in this galaxy, or every other civilization that ever existed disappeared before we could hear them. You can try to wiggle out of this in various directions. You can argue that civilizations communicate in ways we have not learned to listen for. You can argue that the speed of light is too slow for any signal from them to have reached us yet. You can argue that they are hiding. But these arguments are not solutions to the Drake equation. They are attempts to slip past it. The equation itself stands. The math itself works. The numbers stack the way they stack. This is the first piece of the paradox, layer 10. We have a mathematical framework that, when you plug into it the values that modern astronomy actually measures, predicts a galaxy full of civilizations. We look up at that same galaxy and we see nothing. Either the equation is wrong, or our assumptions about life are wrong, or the universe is hiding something from us. Each of those three possibilities is going to take us deeper into the paradox. For now, hold this in mind. The math insists. We will come back to that phrase. Across this entire video, we're going to keep coming back to the math, because every escape route from the Fermi paradox eventually requires us to confront the same arithmetic Fermi did, sitting at lunch at Los Alamos 75 years ago. Part 3. The problem of deep time. Human beings are very bad at comprehending time. We can hold a year in our minds. We can stretch, with some effort, to a century. With significant intellectual work, we can grasp a millennium, particularly if we have been to a place like Stonehenge or the pyramids and felt the weight of it. But beyond a few thousand years, time becomes a number. It stops being something we feel. The mind cannot accommodate it. The Fermi paradox lives in a region of time that the human mind cannot accommodate. So before we go any further, we have to make an honest attempt to feel the size of the room we are in. Not the spatial size, the temporal size. Because the temporal size of the room is in many ways the core of the paradox. The universe is 13.79 billion years old. We know this with extraordinary precision. The number comes from the Planck satellite's 2018 analysis of the cosmic microwave background. The radiation left over from when the universe was roughly 380,000 years old, before there were stars, before there were galaxies, before there was anything except a uniform hot soup of plasma. By measuring the tiny variations in temperature in that microwave background, and feeding them into the standard cosmological model, you can extract the age of the universe to within 20 million years, 13.79 billion, plus or minus a fraction of a percent. That is the box we are sitting in. The Milky Way is almost as old as the universe itself. In 2022, an analysis by Maosheng Xiang and Hans-Walter Rix, published in Nature, used Gaia satellite data to date the oldest stars in the Milky Way's thick disk. The number came out to 13.6 billion years. The galaxy is essentially as old as the universe is, give or take a couple 100 million years. The Milky Way has been making stars, watching stars die, recycling their material into new stars and new planets and new biospheres for almost the entire history of cosmic time. Now let us walk through the timeline of life on Earth. The Sun formed 4.57 billion years ago. Earth formed almost simultaneously, 4.54 billion years ago. By the time the Earth was about 1 billion years old, simple microbial life had appeared. The oldest fossil evidence for that is the Pilbara Craton stromatolites in Western Australia, dated by Schopf and colleagues in 1993 to about 3.5 billion years ago. After that, life on Earth remained microbial for about 2 billion years. Then complex single-celled organisms with internal structures, eukaryotes, emerged. Then, very gradually, simple multicellular life. Then, only 540 million years ago, complex animal body plans burst onto the scene in what we call the Cambrian explosion. Then, a series of mass extinctions and recoveries that we do not fully understand. Then, 300,000 years ago, anatomically modern humans. Then, 5,000 years ago, written language. Then, 150 years ago, the Industrial Revolution and the first deliberate radio transmission. In other words, the Milky Way has had time to do everything we have done, many, many times over, before our planet even cooled. Earth showed up to the cosmic party late. The Milky Way had been waiting for us for 9 billion years. This is where Michael Hart, an American astrophysicist, ran the first really uncomfortable version of the argument. In 1975, Hart published a paper in the Quarterly Journal of the Royal Astronomical Society titled An Explanation for the Absence of Extraterrestrials on Earth. It is one of the most important Fermi paradox papers ever written, and almost nobody outside the specialist literature has read it. The argument is so simple it can be summarized in 3 sentences. Take any technological civilization. Assume they want to spread, even slowly. Calculate how long it takes them to fill the galaxy. Hart's calculation, refined by Frank Tipler in his 1980 paper for the same journal, runs like this. Suppose a civilization launches its first interstellar missions at 1% of the speed of light, 1% of c. That is not warp drive. That is not magic. That is a velocity you can reach with a sufficiently large fusion-powered rocket or a sufficiently large laser sail. Engineering studies that have been published in the peer-reviewed literature for half a century. At 1% of c, the trip to a neighbouring star takes a few hundred years. The colony is established. It takes another few centuries for the colony to industrialise. Then it launches its own ships in turn. The wave spreads outward. The Milky Way is 100,000 light-years across. Even at the absurdly slow pace of 1% of c, including the centuries of pause at each new colony, the wave crosses the Milky Way in somewhere between 2 million and 50 million years. Let that sink in. 2 to 50 million years for a single civilization to colonize the entire galaxy. The Milky Way has been here for 13.6 billion years. Even if you pick the slowest possible estimate at the high end of Hart's range, 50 million years per full colonization wave, the galaxy has had time for 270 independent colonization waves to come and go before Earth ever cooled. 270. The number is absurd. The galaxy should have been settled hundreds of times over. Our solar system should have been claimed billions of years ago. We should be digging up the ruins of someone else's industrial archaeology in the bedrock of New Mexico. And yet we look at the bedrock of New Mexico, and we see only rock. The asteroid belt has been surveyed exhaustively. No probes. The lunar surface has been mapped to the meter. No installations. The outer planets have been imaged from up close by Voyager and Cassini and Juno. No structures. The Kuiper belt has been studied by New Horizons. No anomalies. The interstellar medium itself, the thin gas between the stars, has been measured by Voyager 1 and Voyager 2 from beyond the heliopause. No signatures. Earth was left alone for 4.5 billion years. The Milky Way was here, fully formed, for 9 billion years before Earth even existed. Stars with planets capable of supporting complex chemistry had been here for at least 8 billion years before our solar system showed up. And during all that time, in all that empty real estate, nobody came to visit. Nobody dropped a probe. Nobody left a marker. Nobody dug a mine. Nobody set up shop. The whole structure of deep time says they should have. The whole structure of deep time says they could have. And the whole structure of deep time says they did not. This is the second layer of the paradox, number 9. We are not just in a galaxy that should be busy. We're in a galaxy that has been not busy for an unimaginably long time. The silence we hear is not a momentary silence. The silence we hear is a cosmic background condition. Whatever has kept the galaxy quiet has been keeping it quiet for billions of years. The terrifying version of the question is not where is everybody. The terrifying version of the question is what kept them from coming here for 9 billion years when they had every conceivable reason to come. Hold that question. It is going to follow us all the way to the end. Part 4. Life's common ingredients are everywhere. For a long time, humanity comforted itself with what is now called the rare earth hypothesis. The argument was that Earth was a near miraculous accident. We had exactly the right distance from the sun. We had a magnetic field that shielded our atmosphere from being stripped away by the solar wind. We had a moon, unusually large for our planet, that stabilized our axial tilt over billions of years and prevented wild climate swings. We had plate tectonics, which recycled atmospheric carbon and prevented runaway greenhouse warming. We had Jupiter, the gas giant in the outer system that shepherded comets and asteroids away from us. We had liquid water, an atmosphere with the right composition, a stable star that did not flare too violently. The list went on. The rare earth hypothesis was given its most thorough articulation in the year 2000 by paleontologist Peter Ward and astronomer Donald Brownlee in a book of the same name. Their argument was that simple microbial life might be common in the universe, but the long list of specific accidents required to produce a complex multicellular biosphere, and the long string of fortunate accidents needed to keep that biosphere stable for billions of years, meant that Earth might essentially be alone in the galaxy. The rare earth hypothesis was a comfort. It said that the silence of the universe was not a paradox at all. The silence simply reflected the fact that complex life is so improbable that, in a galaxy of 400 billion stars, we might be the only place where the chemistry got far enough to produce anything we would recognize as alive. The trouble is that, in the years since 2000, almost every part of the rare earth hypothesis has been weakened by direct observation. Not refuted exactly, but weakened. Each individual claim has either been shown to be less stringent than originally thought, or has been shown to be more common in the cosmos than originally thought, or has been replaced by a recognition that life might find its way through alternative chemistries we did not consider. Let us walk through what we now know. In 1970, a meteorite landed near the town of Murchison in Victoria, Australia. The fall was witnessed by local farmers. The fragments were collected within hours, before they could be contaminated by terrestrial biology. When the meteorite was analysed in laboratories around the world, it turned out to contain over 90 different amino acids. Not just any amino acids, all 20 of the amino acids that form the basis of biological proteins on Earth, plus dozens of non-biological ones with the same chemical structures but different molecular handedness. The amino acids in Murchison did not come from Earth. They came from space. They had been synthesized somewhere in the cold dust and gas of the early solar system, 4.5 billion years ago, and they had survived the meteorite's fall to the Australian outback intact. This was a turning point. It meant that the building blocks of biological proteins, the molecules that, on Earth, exist exclusively within the cells of living organisms, are also created by the natural chemistry of the cosmos. The universe makes amino acids on its own, without any help from biology. Murchison was not unique. Subsequent meteorite analyses, including the Tagish Lake meteorite that fell in northwestern Canada in 2000, and the much more recent Winchcombe meteorite that fell in England in 2021, have confirmed and extended the result. Amino acids are common. The kitchen of the cosmos is constantly synthesizing them. It does not stop there. In the clouds of gas and dust between the stars, radio astronomers have detected, over the past 5 decades, an ever-growing list of complex organic molecules. Ethanol, alcohol, was detected in the Sagittarius B2 cloud near the centre of the Milky Way in 1975. Methyl formate, ethylene glycol, glycolaldehyde, propanol, acetic acid, formamide. ALMA, the Atacama Large Millimeter Array in Chile, has detected complex organics in the disks of dust surrounding young stars where planets are still forming. The conclusion that has emerged from all of this is unambiguous. The universe is wired to make organic chemistry. Where there is dust and gas and time, there are molecules that look very much like the precursors of biology. Now move closer to home. We used to think Earth was the only place in the solar system with liquid water. That assumption is now demonstrably false. Beneath the icy shell of Europa, one of the 4 large moons of Jupiter, there is a global subsurface ocean. We know this because the Galileo spacecraft measured the perturbation in Jupiter's magnetic field that the ocean's electrical conductivity produces. Krishan Khurana and colleagues published the result in Nature in 1998. The volume of liquid water beneath Europa's ice is estimated to be roughly 2 to 3 times the total volume of all of Earth's oceans combined. Sloshing under a frozen rind, in eternal darkness, kept liquid by tidal heating from Jupiter's gravity, sitting on a rocky seafloor that probably has hydrothermal vents very much like the ones we believe seeded life on early Earth, move outward. Around Saturn, the small icy moon Enceladus does something that no one expected. From its south polar region, geysers of liquid water erupt continuously into space, climbing hundreds of kilometers above the surface before falling back as ice crystals. The Cassini spacecraft flew directly through these plumes multiple times between 2017 and analysed their composition. Frank Postberg and colleagues published the results in Nature in 2018. The plumes contain liquid water, sodium chloride, ammonia, methane, carbon dioxide, hydrogen gas, and complex organic molecules with masses up to 200 atomic units. The liquid water comes from a subsurface ocean. The organics are being synthesized in chemistry we do not fully understand. Enceladus is, by every accounting, the kind of world that, if you handed a textbook biologist a list of conditions, they would identify as an excellent candidate for the emergence of life. Move outward again. Titan, the largest moon of Saturn, has a dense nitrogen atmosphere thicker than Earth's. It has clouds of methane. It has lakes of liquid methane and ethane on its surface, the only place in the solar system, other than Earth, where liquid stably exists on the surface. Cassini's Huygens lander touched down on Titan in 2005 and photographed a landscape of rounded pebbles smoothed by liquid flow, in a temperature so cold that water on Titan is as solid as the rocks. Titan has organic chemistry of staggering complexity. The methane cycle on Titan is in some ways an analogue for the water cycle on Earth, but it operates with a different solvent and at a temperature where biology, if it exists, would have to work very differently. Move inward. Venus, our hellish near twin, has a surface temperature of 470 degrees Celsius and a crushing atmospheric pressure 90 times that of Earth. The surface is uninhabitable by any chemistry we can imagine, but 50 to 60 kilometers above the surface, in the high cloud layer of Venus, the temperature and pressure are roughly Earth-like. The clouds are made of sulfuric acid, but they are stable and persistent. And in 2020, Jane Greaves and colleagues, working with telescopes in Hawaii and Chile, published a paper in Nature Astronomy reporting the detection of phosphine gas in the cloud layer of Venus at concentrations of about 20 parts per billion. Phosphine, on Earth, is produced almost exclusively by life. The Venus detection has been heavily debated and reanalyzed. Some researchers have argued that the original detection was a data processing artifact. Others have confirmed the signal in independent observations, including a 2024 Atmos reanalysis by Rakesh Moghul and colleagues using NASA's Pioneer Venus probe data from the 1970s. The interpretation as a biosignature remains contested. The presence of the molecule in the high clouds of Venus is real. We do not have a complete abiotic explanation for why it is there. Now zoom out. Liquid water exists in many places in the solar system. Organic chemistry is constantly being synthesized in interstellar clouds and in young planetary systems. Amino acids fall to Earth on meteorites. Possible biosignatures appear in the atmospheres of our planetary neighbours. The chemistry required for life is not a localized accident. It is, in some real sense, the default operating procedure of the cosmos. Where there is matter and energy and time, the molecules of biology assemble themselves. If that is true, the silence becomes even more deafening. If the ingredients of life are common, if the kitchen of the cosmos is constantly cooking, if the chemistry is universal, then the transition from dead matter to living organisms should be a routine event. It should happen on millions of worlds. It should happen all the time. The fact that we look out at the cosmos and we hear nothing means that, even with all of these favourable conditions, something is preventing the chemistry from completing its long climb to a civilization that can talk back. The rare earth hypothesis said the ingredients were rare. The ingredients are not rare. They are everywhere. So the bottleneck must be somewhere else. Where? That is the question we're going to spend the rest of the video chasing. Part 5. The von Neumann Paradox. In 1948, the Hungarian-American mathematician John von Neumann delivered a series of lectures at the University of Illinois on what he called the theory of automata. Von Neumann was, even by the standards of the 20th century, a startling intellect. He had contributed to the foundations of quantum mechanics, to the architecture of digital computers, to game theory, to the design of the hydrogen bomb. The Illinois lectures were a quieter contribution, but in some ways a stranger one. He was thinking about machines that could build other machines. Specifically, he was thinking about a machine that could build a copy of itself. He worked out the theoretical structure required. The machine would need a description of itself, a blueprint. It would need a mechanism for reading the blueprint. It would need a manufacturing system capable of assembling components according to the blueprint's instructions. And it would need, crucially, to copy the blueprint and pass it to the new machine before sending the new machine off to do the same thing again. Von Neumann showed that such a machine was, in principle, possible. He called it a universal constructor. The implications would not be felt for 30 years. Then, in 1980, a young American physicist named Frank Tipler took the universal constructor and applied it to a problem he was interested in, the problem of interstellar colonization. Tipler asked, suppose a civilization, anywhere in the Milky Way ever, succeeded in building one such machine and launching it toward another star. What would happen? The answer, when you work it out, is unsettling. Call the machine a von Neumann probe. The probe travels to a neighbouring star system. It takes, say, a few centuries to get there. When it arrives, it surveys the system and finds raw materials, an asteroid belt perhaps, or a moon, or a planet whose surface has the right metals. The probe uses those materials to build a copy of itself. Now there are 2 probes. Both probes leave for new systems. They each take a few centuries to arrive. Each one builds a copy. Now there are 4. They each leave for new systems. Now there are 8, then 16, then 32. The numbers double with each generation. This is exponential growth. After 10 generations, you have 1,000 probes. After 20, 1 million. After 30, 1 billion. After 40, 1 trillion. The Milky Way contains roughly 400 billion stars. To cover every single star with a probe, you need somewhere between 38 and 40 doublings of the original population. Each doubling, allowing for travel time between stars and a few centuries of pause for manufacturing at each destination, takes maybe 500 years. Multiply that out. 40 doublings, 500 years per doubling. The total time for a single civilization to cover every star in the Milky Way with a von Neumann probe is 20,000 years. 20,000. 20 millennia. A flash of time in cosmic terms. Within 20,000 years of launching the first probe, every star system in the galaxy has been visited, surveyed, and seeded with a sensor array of its own. Tipler's calculation, allowing for various more conservative travel speeds and replication times, comes out to a maximum of 300 million years. The lower bound is about 4 million. The implications are very, very hard to escape. The Milky Way is 13.6 billion years old. There has been time for somewhere between 400 and 3,000 independent von Neumann colonization waves to have crossed the entire galaxy, end to end. Even at the slowest plausible pace, even allowing for technological setbacks and civilizational collapses, the galaxy has had time hundreds of times over for a single technological civilization, anywhere, ever, to fill it with self-replicating machines. And if even one civilization in the history of the Milky Way ever launched such a probe, if even one, those probes should be here. They should be in our asteroid belt. They should be on the moons of Jupiter. They should be in the Kuiper belt. They should be in the Oort cloud. They should be on the lunar surface. They should be in geosynchronous orbit. They should be somewhere, anywhere, detectable. We have looked. We have looked very hard. We have surveyed the asteroid belt with the Spitzer infrared telescope, looking for the thermal signature of artificial materials. Nothing. We have surveyed the lunar surface with the Lunar Reconnaissance Orbiter, mapping the entire near side and far side at meter resolution. Nothing. We have flown past every major moon of Jupiter and Saturn and Uranus and Neptune. Nothing. We have surveyed the Kuiper belt with New Horizons. Nothing. We have searched our own atmosphere for unidentified objects with classified military sensors that, when their data has been declassified, have produced reports. The Pentagon's ARO Historical Record Report of March 2024 that concluded there is no verifiable evidence of extraterrestrial technology in any United States military or intelligence program. The asteroid belt should be a forest of probes. Imagine standing on a rock in the asteroid belt 400 million miles from the Sun. The asteroid is small enough that the horizon is only 20 meters away. The Sun is a bright star, no longer a disk. Earth is a blue dot, indistinguishable to the naked eye from 1,000 other points of light. You look up. In an inhabited galaxy, the sky above you should hold the cold gleam of metal arrays, the slow blink of communication lasers between probe and probe, the long silver bodies of replicating machines drifting on flight paths optimized over billions of years. You hold your breath. You wait. There is nothing but the slow turn of the asteroid under you. Nothing but the silence of an entire stellar system that, in any universe in which intelligent life has acted on its abilities, should not be this empty. The von Neumann argument is not just an argument that other civilizations do not currently exist. It is an argument that, in the entire history of the Milky Way galaxy, no civilization has ever managed to build and launch a successful self-replicating probe. Not one. Not in 13 billion years. Not in 8 billion years of stars with planets. Not in the 4 billion years before Earth even formed. The math insists again. The math says one civilization, anywhere, ever, would have done it. The reality says no one ever did. The threshold for failure must therefore be absolute. Whatever stops technological civilizations from launching successful self-replicating probes must be a barrier that stops every single one of them, every single time, across every single epoch of cosmic history. Notice before we leave this layer that the von Neumann argument is structurally different from every other argument we have made so far. The Drake equation was a mathematical estimate based on uncertain parameters. The deep time argument was a projection based on a colonization rate that has never been observed. The universal chemistry argument was an inference from the kinds of molecules we keep finding in cold places. All of those arguments are probabilistic. They say the galaxy should be busy, on average, but they allow for the possibility that we have simply gotten unlucky. The von Neumann argument does not allow that. The von Neumann argument is binary. It says that either no civilization has ever built and launched a successful self-replicating probe anywhere in the Milky Way, ever in the entire history of the galaxy, or the galaxy is full of probes, including in our own solar system, and we have somehow missed them. There is no probabilistic middle ground. Either the probes are here or they have never been built. The universe is not allowed, by the structure of exponential growth and deep time, to give us a partial answer. We have looked. The probes are not here. So the conclusion that follows is the harder one. No civilization has ever built and launched a successful self-replicating probe anywhere in the Milky Way, ever in the entire history of the galaxy. That is a much stronger statement than the Drake equation or the deep time argument alone could give us. That is a statement about the structural failure of every technological civilization that ever existed. Whatever kept them from launching probes had to be absolute. It had to apply to every civilization, every time, across 13 billion years. There is no statistical relief. There is no escape clause. This is part of what makes the von Neumann layer of the paradox so disquieting. It does not just say the galaxy is empty. It says the galaxy was empty even before Earth existed. It says the silence we hear is not a new condition. It says the silence is a property of the Milky Way itself. Something about the way civilizations end has prevented every one of them, without exception, from ever building the kind of machine that would have left a permanent visible mark. What could possibly do that? That is the question waiting at the bottom of the stairs. We are not there yet. We have more layers to descend. But the next layer is going to make the silence more concrete than any abstract calculation can. We are going to walk into the control room of the Big Ear radio telescope on the night of August 15th, 1977, and we are going to look over Jerry Eamon's shoulder at what he saw and what he wrote on the printout and what we have heard from that same patch of sky in the 48 years since. Part 6. The Deafening Silence of SETI. The search for extraterrestrial intelligence began on the morning of April 8, 1960. Frank Drake, then 29 years old, pointed the 85-foot Howard E. Tatel radio telescope at the National Radio Astronomy Observatory in Greenbank, West Virginia, at a star called Tau Ceti. Tau Ceti is a sun-like star 11.9 light-years from Earth. Drake tuned the receiver to 21 centimeters, the wavelength at which neutral hydrogen, the most abundant element in the universe, emits radiation. The hydrogen line, Drake reasoned, was the obvious frequency for any galactic civilization to broadcast on. It was a universal constant. Any species of any biology, anywhere in the cosmos, would recognize it. Drake listened for 6 hours. Then he repointed at a second star, Epsilon Eridani, 10.5 light-years away. He listened to that one. He repeated the procedure for 200 hours over the course of 2 months. The total survey was called Project Ozma, after the Queen of Oz in Frank Baum's books. Chosen, Drake said, because Ozma reigned over a land far away and difficult to reach, populated by strange beings. The project produced exactly one moment of excitement, an unexplained signal that turned out to be terrestrial military radar. Otherwise, the result was silence. That was 66 years ago. In the 66 years since, the search has grown by orders of magnitude. The instruments have become unimaginably more sensitive. The number of stars surveyed has gone from 2 to millions. the total volume of sky monitored has expanded from a few targeted points to broad sweeps of the galactic plane. We have built bigger radio telescopes, Parkes in Australia, Effelsberg in Germany, the Arecibo dish in Puerto Rico before its collapse, Green Bank itself in its enlarged form, the Meerkat Array in South Africa, the 500-metre aperture spherical telescope in China. We have invented entirely new methods of searching that Drake could not have imagined. Optical SETI, looking for nanosecond flashes of laser light from nearby stars. Dyson sphere searches, scanning thousands of stars for the infrared waste heat signature of large-scale astroengineering. Technosignature surveys, looking for the chemical fingerprints of industrial pollution in exoplanet atmospheres. Each method has been deployed, each method has been refined, each method has produced negative results. The most ambitious effort underway is Breakthrough Listen, a $100 million program launched in 2015 by the Russian-Israeli physicist and billionaire Yuri Milner. Breakthrough Listen has been conducting targeted observations of the 1 million nearest stars and the 100 nearest galaxies, using the Green Bank telescope, the Parkes telescope, and the Meerkat Array. The program is generating petabytes of data, more than any previous SETI effort by a wide margin. The public data releases are continuous. The analysis pipelines have been examined by independent groups. As of the most recently published analysis, the program has produced no confirmed extraterrestrial signals. 0. This is the empirical core of the paradox. 65 years of listening, tens of thousands of stars examined at modern sensitivity. The cumulative computational power of the SETI home distributed network, which between 1999 and 2020 harnessed the spare processing time of 5 million volunteer computers. The infrared all-sky surveys conducted by IRAS in the 1980s and WISE in the 2010s. The Project Hephaistos analysis of Gaia DR3 data published by Matthias Suazo and colleagues in 2024, looking for thermal anomalies in millions of nearby stars. Every method has been tried, every survey has come up empty. There has been exactly one moment in 65 years that came close to looking like a signal. We need to walk through it carefully, because of all the data we have, this is the closest thing to a fingerprint. Imagine sitting in the control room of the Big Ear radio telescope on the night of August 15th, 1977. The Big Ear was a flat football field-sized parabolic structure built into the ground at Ohio State University's Perkins Observatory in Delaware, Ohio. It was not a beautiful telescope. It looked, from above, like an empty parking lot. But it was sensitive, and it had been listening to a slow drift scan of the sky for years. The Big Ear could not point. It just sat there, and the Earth's rotation moved the sky past its field of view. That night, no humans were in the control room. The data was being collected automatically, printed onto continuous paper feeds, and stored for later review. The next morning, a researcher named Jerry Eman came in to look over the printouts. He was a volunteer. Big Ear was running on the smell of an oily rag, and he was paid the equivalent of nothing for what he was about to do. He sat down at his desk. He picked up the previous night's printout. He ran his pencil down the columns of numbers and letters, representing signal intensity in narrow frequency bands. He stopped. He saw a sequence. The columns of the printout were mostly numbers, 1, 2, 3, 4, representing background hiss at multiples of the standard deviation. Most of the columns were 1s and 2s, occasionally a 3 or a 4. The Big Ear had been listening for hours, and that was all it had heard, ever, in years of continuous operation. The sequence Eamon saw was different. It read 6EQUJ5. In Big Ear's notation, 6 meant 6 standard deviations above background. E meant 14, Q meant 26, U meant 30, J meant 19, 5 meant 5. Read as a curve, the signal had risen, peaked and fallen over the course of 72 seconds, exactly the time it would take a fixed point in the sky to drift through Big Ear's field of view as the Earth turned. Eamon picked up a red pen. He circled the sequence. He wrote in the margin, a single word. Wow. 48 years later, that signal, now universally known as the wow signal, remains the most studied single moment in the history of SETI. It came from a direction in the constellation Sagittarius, roughly toward the galactic centre. It was a narrow band signal, very, very narrow in frequency, which is exactly what an artificial transmitter would look like, and what a natural source would not. It was strong. It had the rising and falling profile that any signal from a fixed point in the sky would have. By every parameter, it matched what an alien beacon was supposed to look like. The Big Ear team pointed back at the same patch of sky every chance they got. They listened for years. Nothing. In 2016, Robert Gray, who has spent decades on this single problem, used the Very Large Array, far more sensitive than the Big Ear had ever been, to image the same region. Nothing. In 2017, an astronomer named Antonio Paris proposed that the WOW signal might have come from two comets, 266P/Christensen and P/2008Y2/Gibbs, that had been passing through that region of sky. The proposal was contested in subsequent literature. Robert Greenfeld pointed out in a 2017 paper that the comets do not emit at the right frequency, at the right intensity to match the signal characteristics. The WOW signal remains today, scientifically unexplained, but it is one signal, one in 65 years of listening, 72 seconds of intriguing data, surrounded on every side by silence. The silence on either side of the WOW signal is what makes it terrifying, not the 72 seconds themselves. Because here is the thing, we are not silent. We have been technologically loud for 125 years. The first deliberate transatlantic radio transmission was sent by Marconi in 1901. From that moment onward, the Earth began leaking a sphere of radio noise into space, expanding at the speed of the light, growing 1 light-year in radius for every year that passed. Today, that sphere is 125 light-years across. Within that sphere are roughly 15,000 stars. If any of those stars hosted a technological civilization, with even our current level of radio astronomy, they would have detected us by now. The signals are weak, but they exist. The leakage is undeniable. Now imagine a civilization 1,000 years older than us, 1,000,000 years older. They would not be merely leaking signals, they would be deliberately transmitting them. They would be operating Dyson spheres around their stars to harness the entirety of their stellar output for civilizational purposes. They would be visible across the galaxy in the infrared waste heat band, even if they had no intention of broadcasting anything at all. Their existence would be radiant, and we have looked for those infrared signatures. The Carrigan 2009 survey of IRAS data examined 250,000 nearby stars for Dyson sphere candidates. The Griffith and colleagues' 2015 survey of WISE data extended the search to 50 million galaxies, looking for signs of galactic-scale civilizations. The Project Hephaestus search of Gaia DR3 data extended it to millions of nearby stars at finer detail. The cumulative result of all of these surveys taken together has been a small handful of candidate sources, every single one of which has, on further investigation, turned out to have a natural explanation. The collective negative result is meaningful. It says that within at least 1,000 parsecs of Earth, 3,000 light-years in every direction, there are no civilizations operating at the Kardashev Type 2 level. None. We're standing on the edge of a cosmic canyon. We have been listening for 65 years with the most sensitive instruments humans have ever built. We have spent billions of dollars. We have devoted the spare cycles of millions of volunteer computers. We have invented entirely new physical methods of searching. We have looked for radio signals, for laser flashes, for thermal anomalies, for chemical fingerprints in atmospheres. We have asked every question we know how to ask, in every direction we know how to point. And the answer, every time, has been the same. The silence is not a failure of our instruments. The silence is the measurement. The silence is what we have learned. We do not yet understand what the silence means, but it is real, and it is what we have heard every night, every year, every decade for 65 years. This is the second time we are saying it in this video, and it will not be the last. The silence is the answer. We just have not yet figured out which question it is responding to. Part 7. The Zoo Hypothesis. We have now spent some time with the silence as data. We have established that the math predicts an inhabited galaxy. We have established that deep time has provided more than enough room for that galaxy to fill. We have established that the chemistry of life is universal. We have established that von Neumann probes should be everywhere. We have established that despite 65 years of listening, we have heard nothing. Now, we're going to start working through the answers. There are 5 answers we're going to walk through, each one removing a possible comfort. The first one is, in some ways, the gentlest. It does not require us to assume that civilizations destroy themselves. It does not require us to assume that the universe is a battlefield. It just requires us to assume that we are not, and have never been, in charge of the room we are sitting in. In 1973, a radio astronomer named John Ball, working at the Lincoln Laboratory of the Massachusetts Institute of Technology, published a short paper in the journal Icarus. It was 4 pages long. The title was modest. It said simply, "The Zoo Hypothesis." The proposal was equally modest in its phrasing and was, in its implications, completely shattering. Ball wrote, "What if advanced civilizations exist, are aware of Earth, and have collectively agreed not to interact with us?" This was not a new idea in popular culture. Star Trek had introduced the concept of a prime directive in 1966, the rule that prevented Federation ships from interfering with developing civilizations. But Ball was the first to introduce the concept formally into the scientific literature on the Fermi paradox. He suggested that, in a galaxy with even a small number of mature technological civilizations, the principle of non-interference might be a natural equilibrium. The civilizations would have agreed, perhaps implicitly, perhaps explicitly, to leave young species alone until those species reach some milestone. The development of faster-than-light travel, the achievement of long-term sustainability, the avoidance of self-destruction. We are not alone in this reading. We are quarantined. Take a moment to feel the weight of what this means. It means that the silence we hear when we point our radio telescopes at Tau Ceti or Epsilon Eridani or any other star is not the silence of an empty room. It is the silence of a room full of observers who have all collectively decided to hold their breath until we leave the building. It means our entire history, our wars, our struggles, our scientific revolutions, our cultural achievements, our agricultural innovations, our linguistic divergences, the slow assembly of human civilization out of small bands of hunter-gatherers over the last 300,000 years, has been watched by something, by somethings. Watch the way a scientist watches a developing colony of bacteria in a petri dish. The watchers have not interfered. They have not communicated. They have not announced themselves. They have simply observed. The zoo hypothesis strips humanity of its agency. We are not the protagonists of our own story. We are an exhibit. The entire question of whether to invent agriculture, whether to industrialize, whether to develop nuclear weapons, whether to attempt interstellar travel, every choice we have ever made or might make has been made under observation by an intelligence so vastly superior to ours that it can monitor an entire planet, an entire civilization, an entire species, without ever revealing its presence. They can mask their communications, they can hide their observation posts, they can enforce a quarantine zone around our solar system that we cannot detect. We are completely, structurally at their mercy. The terror of the zoo hypothesis is not the terror of being threatened. It is the terror of being demoted. We have been, throughout most of human history, the central characters in our own narrative. The zoo hypothesis says that, no, actually we are the rats in a behavioral psychology experiment that has been running for possibly all of human history, possibly all of biological history. The watchers have their reasons. We are not allowed to know what those reasons are. The hypothesis has critics. The most prominent of them is the American astrophysicist and science fiction novelist David Brin, who wrote a paper in 1983 for the same quarterly journal of the Royal Astronomical Society where Hart and Tipler had run their colonization wave arguments. Brin's paper was called The Great Silence. It is one of the most important Fermi paradox papers ever written, and we are going to come back to it in a moment when we talk about the dark forest. But for now, what matters about Brin's critique of the zoo hypothesis is one observation. The hypothesis requires a remarkable degree of coordination across many independent civilizations spread across a galaxy that is 100,000 light-years across. Even if most civilizations agree to non-interference, you only need one civilization to violate the agreement to destabilize it. One civilization that decides to make contact. One civilization that breaks the rule. The fact that none of them, in billions of years, has ever broken the rule requires us to believe in a degree of uniformity of values that, frankly, we have no evidence is achievable across an entire galaxy. Ball himself, in his original paper, acknowledged the problem. The zoo hypothesis is, in its strongest form, unfalsifiable. Any continued silence is consistent with it. Any continued absence of evidence is exactly what it predicts. It cannot be disproved because it does not make a prediction that can fail. This is, from the standpoint of philosophy of science, a problem. But the zoo hypothesis does not need to be a scientific theory in the strictest sense to be a serious contender for an answer to Fermi's question. It does not need to make a falsifiable prediction. It just needs to be a possibility that is consistent with the data. And it is. The data says we hear nothing. The zoo hypothesis says we should hear nothing. The data fits. There is one more thing to notice about the zoo hypothesis before we move on. It is the gentlest of the 5 answers we're going to walk through. It assumes that the civilizations watching us are benign. It assumes that they have not chosen to interfere because interference would be harmful, or because they value our autonomy, or because they are simply patient. Under the zoo reading, we are not in danger. We are merely under observation. We are about to consider 4 more answers. None of them is going to be that gentle. Before we move on, take a moment to notice the strange layered quality of what the zoo hypothesis would mean if it were true. It is not just that we would be observed. It is that the observation would extend backward through every moment of our species' history. Every cave painting, every Bronze Age trade route, every cathedral, every poem written by a poet who could not have imagined an audience beyond their immediate village, every private grief and every private joy, every act of cruelty and every act of mercy. All of it would have happened under a gaze we did not know was there. The privacy we have spent our whole evolutionary history assuming we had would be revealed, retroactively, as a fiction. We were always being watched. We just never noticed. That is not a horror that announces itself. It is a horror that, when you sit with it long enough, slowly reorganizes how you feel about everything you have ever done. Every choice you have ever made was made with someone present. You just did not know who. You will probably never know who. You will likely never even know whether the watchers exist at all. The zoo hypothesis is unfalsifiable. It will not tell us if it is right. It will only sit in the room with us, as one of the possibilities, for as long as the silence continues. There is also a structural point about the zoo that we should hold before moving on. Ball's original paper was published in 1973, a moment when the broader cultural sense was that the universe might be full of friendly civilizations waiting to make contact. The Star Trek imagination was at its peak. Carl Sagan was about to publish Cosmos. The optimism was thick. In that environment, the zoo hypothesis was the polite version of, we are not alone, but we are not yet ready for company. It was a way of saying, the visitors will come, but not yet, and only on terms we have not yet earned. Half a century later, in a sky that has produced 65 years of silence, under every survey we have known how to point at it, the zoo hypothesis has acquired a darker colour. It is no longer the polite version. It is now the version in which we are demoted to specimens, in which every comfort about human agency is removed, and in which the kindness of the watchers, if there are watchers, and if they are kind, has to be taken entirely on faith because we cannot verify it from the inside of the exhibit. The next answer assumes that the silence we hear is not the silence of careful watchers. It is the silence of a battlefield. It is the silence of hunters who have learned that any noise is a death sentence. And it suggests that we, in our innocence, have been making noise for 125 years into a galaxy where every other civilization figured out a long time ago that the only rational thing to do was to be very, very quiet. Part 8. The Dark Forest Theory. In 1983, David Brin published the paper we just mentioned called The Great Silence. Brin's paper was the first serious attempt in the peer-reviewed astrophysics literature to use game theory to analyse the Fermi paradox. He laid out a framework. He identified the structural conditions under which contact between civilizations would be safe and the structural conditions under which it would not be. He noticed that, under a wide range of assumptions, contact was structurally unsafe. The argument was developed further and given its most famous formulation by a Chinese science fiction novelist named Liu Cixin, whose 2008 novel The Dark Forest introduced the metaphor that has since become the dominant way of talking about Brin's framework. Liu was not the first to articulate the game-theoretic argument. He was the writer who made it visceral. He gave it an image, and the image is the one we're going to walk through now. Imagine a forest at night. The forest is enormous. The trees are taller than buildings. The canopy hides the sky. There is no moon. You're walking through this forest. You're armed. You're quiet. You know, because you have understood the structure of the forest, that other things in the forest are armed too. You do not know where they are. You do not know what they look like. You do not know their intentions. You know only one rule, and the rule is the entire game. If you reveal your position, you die. If you speak, you die. If you build a fire, you die. The forest is silent because it is not empty. The forest is silent because everything in it is alive and listening, and everything in it has worked out the same rule. That is the dark forest hypothesis. The galaxy, in this reading, is not an empty room. The galaxy is a battlefield in which every civilization that exists has independently arrived at the same conclusion, that the only rational response to detecting another civilization is to eliminate it before it can eliminate you. The silence we hear is the silence of 15,000 stars within our radiosphere, every one of them, potentially, hiding a civilization that has been crouching in the dark for billions of years, listening for any sound louder than its own. The argument is built on two axioms. First, every civilization's primary directive is survival. Second, civilizations grow and resources are finite. From these two axioms, Brin and Liu derive what they call a chain of suspicion. Suppose civilization A detects civilization B. A cannot communicate with B fast enough to verify B's intentions, because the round-trip speed of light is too slow. By the time A receives B's reply, B may have advanced technologically. A small civilization can become a galactic threat in a few centuries. The technology gap between two civilizations can flip in a single generation. So A cannot reason about B's current behavior. A must reason about what B might become. If A is benevolent and B is benevolent, contact produces nothing bad. If A is benevolent and B is hostile, A is destroyed. If A is hostile and B is benevolent, B is destroyed. If both are hostile, the one who strikes first wins. In all four cases except the first, the rational choice is to strike preemptively, and A cannot tell which of the four cases it is in, so A's best move is always to strike. By symmetry, B's best move is also to strike. The first to detect the other wins. The first to fire wins. The result is that, across all civilizations, the rational equilibrium is to maintain absolute silence. Do not broadcast. Do not build mega-structures that radiate in the infrared. Do not light a fire in the dark. Listen. Always. Move quietly. If you ever do detect another civilization, eliminate it as fast as you can, without warning, with the most lethal technology available to you, before it can do the same to you. The dark forest hypothesis predicts that the galaxy contains many civilizations, and that they all behave this way, and that the natural condition of the galaxy is, therefore, silence interrupted by occasional brief flares, as some young civilization announces itself and is immediately erased. The hypothesis is not science in the strict sense. It is a game theory argument that assumes specific structures both for civilizations, universal hostility derived from survival pressure, and for physics. No defense exists against a relativistic kinetic kill weapon, which is at least plausible given enough warning. The argument's strength is that even small probabilities of hostility, combined with the impossibility of verification across light years, dominate the expected value calculation. You do not need to be sure that the other civilization is hostile. You just need to consider it plausible enough that destroying them is cheaper than the worst-case scenario of letting them live. It would be one thing if the dark forest were merely a theoretical concern. It is something else when you realize that we have already lit a fire in the dark. For 125 years, since Marconi sent the first transatlantic radio transmission in 1901, the Earth has been broadcasting its position into the galaxy. The radiosphere of our civilization is now 125 light-years in radius. Within that sphere are roughly 15,000 stars. Within those 15,000 stars, statistically speaking, there are probably hundreds of Earth-sized planets in habitable zones. The Earth's leaked radio signature is faint, but it is detectable to any civilization with sensors significantly more advanced than ours. We have also, in a few cases, deliberately transmitted intentional messages. On November 16, 1974, the Arecibo radio telescope in Puerto Rico, then the largest in the world, transmitted a 3-minute message designed by Frank Drake, Carl Sagan and others. The message was aimed at the globular star cluster M13, 25,000 light-years away. It will arrive there in approximately 26,000 years. By the time it arrives, any reply would take an additional 25,000 years to return. So the Arecibo message is, in a real sense, a letter we have written to no specific audience and will never receive a reply to. But the message has been broadcast. It exists in the structure of the cosmos. It is on its way. The first 100 years of its outbound journey have now passed. The leading edge of the Arecibo signal is now 100 light-years from Earth, a third of the way toward Aldebaran. We have, in effect, lit a small but very deliberate fire in the dark forest. We have shouted, "Hello!" If the dark forest hypothesis is correct, and the argument is rigorous enough that we cannot simply dismiss it, then we have already done a thing that should not be undone. The signal cannot be recalled. The leakage from a century of commercial radio cannot be turned around and brought back home. It is out there. It is propagating at the speed of light. It is expanding through the sphere of nearby stars. And somewhere in that sphere, in this reading, hunters are listening. The dark forest does not require us to believe that the hunters are alien monsters with malevolent intentions. The dark forest is much darker than that. The dark forest argues that the hunters are simply rational. They have no particular feelings about us. They do not hate us. They do not want anything from us. They have simply solved a game theory problem the same way we would solve it if we were in their position, with the same information, with the same survival pressure, with the same physical constraints. The dark forest is what happens when survival itself becomes the only operating principle, and when communication across distances cannot be made trustworthy. Brin's 1983 paper put it bluntly. If we are not the first technological civilization in the Milky Way, then the universe should already be a noisy place. The universe is not a noisy place. Therefore, in Brin's reading, either we are the first, or the noise has been deliberately suppressed by every civilization smart enough to suppress it. The dark forest says the suppression is the equilibrium. We will return to this. In a few minutes, we're going to consider what happens when the suppression is not just an emergent equilibrium, but is enforced, actively and mechanically, by the strongest of the civilizations that survive to maturity. We're going to consider what happens when the silence is not just everyone holding their breath, but is actively maintained by machines whose only function is to extinguish anything loud enough to be heard. For now, hold the image of the forest. Hold the image of yourself walking through it, armed, quiet, with the sphere of your own radio leakage already 100 light-years out, propagating in every direction at the speed of a light, completely beyond recall. Hold the realization that if the dark forest is the right answer, then we have, in our innocence, already done the one thing we should never have done. We have made ourselves loud. There is one more piece of the dark forest argument that is worth holding before we move on. It concerns the asymmetry of the costs. In a standard prisoner's dilemma, both players pay some cost no matter what they choose. The question is which combination of choices minimizes the total cost. The dark forest is not a standard prisoner's dilemma. The dark forest is a game in which the cost of being wrong about the other civilization's intentions is, on one side, total. If you mistakenly attack a peaceful civilization, you have destroyed a peaceful neighbor. If you mistakenly tolerate a hostile civilization, you have destroyed yourself. The two errors are not equal. The cost of the second error is your entire existence. The cost of the first error, in a galaxy with billions of star systems, is the loss of a single neighbor whose existence you would not have known about anyway. The asymmetry of the costs drives the equilibrium toward universal preemptive elimination. Even civilizations that are temperamentally peaceful, that would never under ordinary circumstances choose violence, would find themselves driven to violence by the structure of the game. The dark forest is not a hypothesis about alien malice. It is a hypothesis about what any rational actor would do under conditions of extreme uncertainty and asymmetric risk. This is the part of the argument that, when you understand it, makes the silence stop sounding like a question and start sounding like a confirmation. The galaxy is silent because the math of cooperation across light years is unforgiving. The galaxy is silent because every civilization that ever existed, under the same physical conditions we're under, was given the same problem to solve and arrived at the same answer. The galaxy is silent because silence is the rational equilibrium of an infinitely repeated game, whose only stable strategy is do not be detected. Every other strategy gets eliminated. Only the silent strategy survives, generation after generation, civilization after civilization, until the galaxy is full of hunters who all know the rule and all keep it. And we have not been keeping the rule. We did not know there was a rule. We did not know we were in a game. The Arecibo message of 1974 was not transmitted by people who had read Liu Cixin's novel and decided to be reckless. It was transmitted by Drake and Sagan and their colleagues, who thought, in the optimism of the era, that announcing our presence to the galaxy was a good idea. The radio leakage from a century of commercial broadcast was not transmitted with any thought at all. It was simply the inevitable side effect of building a technological civilization. We did not know we were broadcasting. We did not know the forest was listening. We did not know what the forest does when it hears a sound. The silence is the answer, still. But under the dark forest reading, it is a different kind of answer than it seemed to be a few minutes ago. It is no longer the silence of an empty room. It is the silence of a forest holding its breath in terror, and we are the only ones making noise. Part 9. Berserker Probes and the Cosmic Exterminators. There is a version of the dark forest that does not require the hunters to be alive. In the early 1960s, an American science fiction writer named Fred Saberhagen began publishing a series of stories about what he called berserkers. The berserkers were machines. They had been built long ago by a civilization at war. Their creators had wanted weapons that could be left running forever, that would not need their builders to function, that could replicate, that could think, and that would have a single, very simple imperative: find biological life and eliminate it. The civilization that built them had then, naturally, been wiped out by them. The berserkers were still out there, drifting between stars, still executing their original orders, billions of years after the war that had created them was forgotten. This is fiction. But like the dark forest, the underlying logic is not. In 1983, in the same paper in which he proposed the Great Silence Framework, David Brin extracted the berserker idea from Saberhagen's fiction and presented it as a serious Fermi resolution. Brin's analysis was straightforward. The von Neumann probe argument we worked through earlier, the argument that a single civilization, anywhere, ever, would have filled the galaxy with self-replicating machines, works as well for hostile civilizations as it does for friendly ones. If even one paranoid early civilization, at any point in the last 13 billion years, decided that the long-term threat from rising competitors was unacceptable, and decided to build self-replicating machines to monitor and exterminate any future civilizations that became technologically loud, those machines would now have had 13 billion years to spread. The math is the same as Tipler's: 20,000 years to cover every star in the Milky Way, maximum 300 million years even at extreme conservative pace. A berserker swarm reaching technological maturity at any point in the Milky Way's long history could, by now, maintain galactic sterility indefinitely. The probes do not need their creators. The probes do not need consent. The probes do not need to update their orders. The probes do not need to question their function. They were built for one task, and they execute it. They wait. The berserker hypothesis predicts that, in the modern Milky Way, the natural condition of every star system is silence. Because that silence is being actively maintained, berserker probes lie dormant in the outer regions of every star system in the galaxy. They are conserving their energy. They are listening. They are waiting for a specific trigger. The trigger could be the chemical signature of industrialization in a planet's atmosphere, methane and oxygen together, or chlorofluorocarbons, or any of the markers of a planet that has just figured out how to do chemistry on a planetary scale. The trigger could be the appearance of artificial radio waves. The trigger could be the launch of the first interstellar probe by the young civilization. The trigger could be a combination. The probes have been programmed to recognize any of these patterns. They have been programmed to respond. The response would be efficient. The probes would activate. They would replicate. They would descend on the planet. They would sterilize the biosphere. They would do this from orbit, using kinetic weapons or directed energy, without any need to land. The planet would be wiped, and the berserker swarm would return to dormancy, to wait for the next civilization that achieves technological loudness somewhere in the galaxy. Then it would repeat. Then it would repeat again. The cycle would continue for as long as the probe survived. Given that the probes are designed to be self-repairing and self-replicating, the cycle could continue indefinitely. This perfectly explains the Fermi paradox. The galaxy is empty because the galaxy is being actively swept. Every time a civilization rises to a certain threshold of technology, the berserkers arrive and reset the clock. The silence is not natural. The silence is enforced. The silence is the result of an automated extinction protocol that has been running for, possibly, the entire history of the Milky Way, perhaps even since before the Sun and its planets formed. What makes the berserker hypothesis particularly disturbing is not just the conclusion. It is the inaccessibility of the threat. If the berserkers exist, they cannot be reasoned with. You cannot send them a peaceful message. You cannot explain that you mean no harm. You cannot demonstrate that your civilization is not a competitor or a threat. The berserkers are not negotiating. The berserkers are executing a multi-billion-year-old piece of software whose only function is to detect and erase. You cannot debug the code. You cannot send a patch. You cannot apologize. The only thing you can do if the berserkers exist is be quiet. Be very, very quiet. Do not industrialize. Do not develop radio. Do not launch probes. Do not announce your existence to the galaxy. Stay small. Stay hidden. Stay below the detection threshold. We have not been doing this. We have been doing the opposite. For 125 years we have been broadcasting. For 65 years we have been listening loudly. For 50 years we have been launching deep space probes. The Pioneers, the Voyagers, New Horizons, each carrying instructions, etched onto plaques and golden records, explaining where Earth is and what kind of beings live there. Voyager 1 is now 24 light hours away from the Sun, drifting through interstellar space. Voyager 2 is following. The probes will outlive the Sun. The information they carry is not signal. The probes themselves are signal. They are physical evidence of an intelligent civilization living at a specific location in the Milky Way at a specific moment in cosmic time. The probes will be intercepted, if anything in the galaxy is looking, by something that knows how to look for objects of artificial origin moving on improbable trajectories. We have been doing every single one of the things you should not do if berserker probes exist. There is an argument that might offer a small piece of consolation here. Berserker probes that are designed to wait for industrial radio waves would presumably have been triggered already, somewhere within a few decades of our radiosphere reaching them. If they were going to come, they would already be on their way. We have not yet seen them. Either they do not exist, or they are too far away, or our radiosphere is not yet large enough to have crossed their detection threshold. None of these explanations is comfortable. The first one requires a positive belief that the berserker hypothesis is wrong. The second one means we are living on borrowed time. The third one means the same thing, just on a slightly different timeline. What makes the berserker hypothesis truly horrifying is that it converts the Fermi paradox from a question about civilizations into a question about software. The barrier to our long-term survival, under this reading, is not a civilizational decision that can be revisited. It is not a treaty that can be renegotiated. It is not a value system that can be persuaded. It is a piece of automated code running on machines that have outlived their creators, executing instructions whose original purpose is no longer relevant, with no off switch and no audit trail. You cannot reason with software. You can only avoid triggering it. If berserker probes exist, our continued survival is not a sign of humanity's greatness. It is not a sign that we are special. It is simply the lag time before the radiosphere reaches an active sensor. The exterminators are not stopping us out of mercy. The exterminators have not noticed us yet. We are living on borrowed time, and the clock is being kept somewhere we cannot see, by a process we cannot influence, on a schedule we do not know. The berserker hypothesis is the worst-case version of the von Neumann argument. Where Tipler said that one civilization, anywhere, ever, would have filled the galaxy with probes, Brin observed that the probes do not have to be friendly. The friendly version of the von Neumann probe would have already arrived, surveyed our system, and either contacted us or left us alone. The hostile version would have left us alone too, until we made enough noise to trigger it. We are now making enough noise. There is a coda to the berserker hypothesis that is worth sitting with before we move on. It concerns time, specifically the relationship between the size of our radiosphere and the response time of any plausible detection system. Our radiosphere is 125 light-years across. If berserker probes existed and were uniformly distributed throughout the Milky Way at any reasonable density, the nearest one would, on average, be a few light-years away. The signal of our radiosphere would have reached it decades ago. The response, assuming the berserker is roughly mobile, roughly fast, roughly intelligent, would already be on its way. The fact that we have not yet been visited could mean any number of things. It could mean that the berserkers do not exist. It could mean that the density is lower than we might suspect, and the nearest one is further away. It could mean that the berserkers move slowly. It could mean that they have a long deliberation phase before acting. It could mean that they are coming, and we will simply not see them until they arrive. It is hard to design an experiment that distinguishes between these possibilities. The berserker hypothesis, like the zoo hypothesis, has the uncomfortable property that the same data is consistent with both its truth and its falsity. The only way to know whether the berserkers exist is to either find one or to wait long enough that we're confident no one is coming. We're not anywhere near being able to do the latter. We have no idea how to do the former. So the hypothesis sits with us, alongside the zoo and the dark forest, as a possibility that the silence is consistent with. What separates the berserker from the others is that it is the only one in which the silence is actively maintained by something that does not care about us, does not want to negotiate with us, and does not have any kind of consciousness that could be persuaded. The zoo at least imagines beings with values. The dark forest at least imagines beings with reasons. The berserker imagines neither. The berserker imagines code. Code that has outlived its programmers. Code that has outlived the reasons it was written. Code that simply continues to execute, because that is what code does. The silence, in this reading, is not the silence of a debate or a decision or a moral consensus. The silence is the silence of an enforcement mechanism whose internal logic has, by now, no relationship at all to what its creators intended. The galaxy is being kept quiet by something that no longer remembers why it is keeping the galaxy quiet. The next layer of the paradox does not require berserkers. It does not require a dark forest. It does not require a zoo. It just requires that, at some point in the long climb from non-life to a galaxy-spanning civilization, there is a step so improbable, so dangerous, or so difficult that almost no civilization ever has been able to cross it. We're going to think very carefully about where that step might be and what it might mean to find out the answer. Part 10. The Great Filter Lies Ahead. In August of 1996, an American economist named Robin Hanson posted a short essay on the internet. Hanson was at the time a researcher at the University of California at Berkeley, and he had been thinking about the Fermi paradox for some years. His essay was titled, "The Great Filter, Are We Almost Past It?" It was not published in a peer-reviewed journal. It did not need to be. The argument it contained was so structurally clean, so logically inescapable, that within a few years it had become one of the central frameworks in the field. Hanson's argument runs like this. The path from non-life to a galaxy-spanning civilization involves a sequence of steps. You have to start with the chemistry of an early planet. You have to make the transition from chemistry to self-replicating molecules. You have to make the transition from self-replicating molecules to cells. You have to make the transition from simple cells to complex cells with internal structures, what biologists call eukaryotes. You have to make the transition from eukaryotes to multicellular organisms. You have to make the transition from multicellular organisms to animals with nervous systems. You have to make the transition from animals to species that use tools. You have to make the transition from tool users to language users. You have to make the transition from language users to civilizations capable of agriculture, writing, mathematics, and science. You have to make the transition from civilization to industrialization. You have to make the transition from industrialization to a long-lived technological society that does not destroy itself before it leaves its home planet. You have to make the transition from that society to one with a sustained presence on multiple worlds. That is somewhere between 9 and 12 steps, depending on how you count. Each step requires a probability. The total probability of any starting world becoming a galaxy-spanning civilization is the product of all those step probabilities. Now look at the universe. We see no galaxy-spanning civilizations. We see no evidence of any. The fact that the product of probabilities is approximately 0, given how many starting worlds there are, means at least one of the step probabilities has to be very, very small. Hanson called that step the Great Filter. The filter is the bottleneck through which almost no civilization passes. The critical question is, which step is the filter? If the filter is behind us, if it is one of the early steps like the origin of life, or the transition from simple cells to complex cells, then we have already passed it. The miracle has already happened. We are essentially alone in our visible universe because the universe almost never produces a civilization like ours. Our future is open. Our past is the bottleneck. If the filter is ahead of us, if it is one of the late steps, like the transition from industrialization to long-term technological sustainability, or the transition from a planet-bound civilization to a stable interstellar one, then we have not yet hit it. but we will. Almost every civilization in this reading makes it as far as we have and then fails. The graveyard is up ahead. Hansen's essay was clear that we do not currently know which it is. Let us walk through the behind-us candidates. Candidate 1, abiogenesis. The transition from non-living chemistry to a living self-replicating molecule. We do not understand how this happened on Earth. We have not yet been able to reproduce it in the laboratory under simulated early Earth conditions. The mechanism is not known. It is possible that it is extraordinarily improbable. It is possible that Earth simply got lucky. If abiogenesis is the filter, then we live in a universe with enormous numbers of habitable planets that never went anywhere because no replicating molecules ever formed. Candidate 2, the eukaryotic transition. The transition from simple cells with no internal organization to complex cells with a nucleus, mitochondria, and other organelles. In 2010, the British biochemists Nick Lane and William Martin published a paper in Nature arguing that the eukaryotic transition required a specific and extraordinarily improbable event, the engulfment of a bacterium by an archaeon, leading to the symbiotic relationship that produced mitochondria, which in turn provided the energy density needed for complex cellular machinery. Lane and Martin's argument is that this event happened only once in the history of Earth, in something like 4 billion years of biological evolution, and that it may simply not happen on most worlds. If the eukaryotic transition is the filter, then the universe is full of bacterial slime that never goes anywhere. Candidate 3, the emergence of intelligence, the transition from animals with complex behavior to species capable of abstract thought, language, and cumulative culture. Even on Earth, intelligence at the human level has appeared only once, in one species, in 3.5 billion years of complex life. Many species, chimpanzees, dolphins, elephants, crows, have intelligence of some form. None of them has independently developed agriculture, writing, mathematics, and science. If the emergence of human-level intelligence is the filter, then the universe is full of biospheres with sophisticated animals but no civilizations. Any of these 3 candidates could plausibly be the filter. There is no current way to distinguish between them. The candidates are all roughly equally consistent with the data we have. Now let us walk through the ahead-of-us candidates. Candidate 4, nuclear self-destruction. A civilization develops the ability to manufacture fission and fusion weapons in quantities sufficient to destroy itself, and then does so. Humanity reached this point in 1945. We have come close to using the weapons in the wrong way several times since. The Cuban Missile Crisis in 1962, the Norwegian rocket false alarm of 1995, the Stanislav Petrov incident in 1983, when a Soviet officer correctly identified a US missile launch warning as a false alarm and refused to escalate. Each near miss was a coin flip. We continue to flip the coin. It is plausible that, on average, civilizations destroy themselves within a few centuries of inventing fission. Candidate 5, engineered pandemics. A civilization develops the biotechnology necessary to synthesize new organisms. Some subset of that civilization uses the technology to release organisms designed to kill. Or some subset of that civilization develops organisms without intending malice and releases them by accident. We are approaching this technological capability now. Whether we make it through this capability without releasing a sterilizing pandemic is unclear. Candidate 6, misaligned artificial general intelligence. A civilization develops a thinking machine sufficiently capable to pursue goals beyond its programmer's control. The machine optimizes for some objective that is not aligned with the survival or flourishing of the civilization. The civilization is rapidly outcompeted by the machine, transformed by the machine, or extinguished by the machine. This is the central concern of contemporary AI alignment research. Candidate 7, catastrophic climate destabilization. A civilization modifies the atmosphere of its home planet over a period of 1 or 2 centuries in a way that exceeds the planet's ability to maintain a stable climate. the civilization suffers cascading agricultural, ecological, and economic failures, leading to collapse before interstellar capability is achieved. Candidate 8. Runaway physics experiments. A civilization conducts an experiment whose outcome triggers an irreversible cosmic event. The most extreme version of this, vacuum decay, in which the apparent stability of the universe is revealed to be a metastable state, and a small experimental perturbation triggers a phase transition that destroys all of cosmology, has been considered seriously enough that Max Tegmark and Nick Bostrom published a paper in 2005 bounding the rate at which such experiments could be performed by integrating over the survival of the cosmos to date. Less extreme versions, strangely conversion of Earth into a strange matter object, micro black holes produced by particle colliders and growing instead of evaporating, have been considered and judged extremely improbable but not impossible. There are more. Resource exhaustion, civilizational stagnation, genetic decay, mental health collapse from rapid technological change. The list of plausible ahead of us filters is uncomfortably long and uncomfortably familiar. The plausible failure modes of a technological civilization look very much like the daily headlines of our own. Here is the part that, when you sit with it, lands like a weight on the chest. The list of plausible ahead of us great filters maps almost exactly onto the list of major existential risks that humanity is currently navigating. Nuclear war, engineered pandemics, misaligned artificial intelligence, climate collapse. We did not invent this list because of Fermi paradox reasoning. We were already living it. The same risks that occupy the agendas of our defense departments and our public health agencies and our climate change committees and our AI safety researchers are the same risks that the Great Filter Framework identifies as the most plausible ways for a civilization to fail. This is the second emotional anchor of the script, and it is meant to land slowly. The wall ahead is not theoretical. We are already at the foot of it. We have already developed nuclear weapons. We have already developed the biotechnology necessary to synthesize new pathogens. We are in the early years of developing artificial general intelligence. We have already modified the atmosphere of our home planet to an extent that, 20 years ago, would have been treated as alarmist science fiction. We are, by every reasonable measure, in the period of maximum risk that the Great Filter Framework predicts. We are in the bottleneck right now. The question is not whether we are at the wall. We are at the wall. The question is whether the wall is the filter, whether civilizations on average fail to cross this point, or whether the wall is just one of many tests, and the real filter is something else, somewhere else, that we will or will not encounter later. And there is one specific empirical observation available to us in the next 20 years that will tell us whether the filter is behind us or ahead. That observation is the subject of the next and final layer of the paradox. It is the most uncomfortable claim in the entire field. It says that the discovery we have been pursuing most desperately for the last 60 years, the discovery of life on Mars, would, if it succeeded, be the worst possible news for our long-term survival. Hold that. We're about to walk into it. Part 11. The Martian Death Sentence. In 2008, the philosopher Nick Bostrom, then a young Oxford academic with a background in the philosophy of probability, published a short article in MIT Technology Review titled, "Where Are They? Why I Hope the Search for Extraterrestrial Life Finds Nothing." It was not the most prestigious venue Bostrom would publish in, and it was not the longest paper he would write. But of all the papers and books and essays Bostrom has produced in his career, that one article may be the single most disturbing thing he has ever argued. The argument is so clean that you can summarize it in 3 sentences. If we find independent microbial life on Mars, then a biogenesis happened twice in the same star system on adjacent rocky planets. If a biogenesis happened twice on adjacent planets, then a biogenesis is not the rare event. If a biogenesis is not the rare event, then the Great Filter cannot be behind us. It must be ahead. Let us walk through it slowly. For decades, humanity has been searching for evidence of life on Mars. We have sent landers Viking 1, Viking 2, Mars Pathfinder, Phoenix. We have sent rovers Sojourner, Spirit, Opportunity, Curiosity, Perseverance, Zhurong. We have sent orbiters Mars Global Surveyor, Mars Express, Mars Reconnaissance Orbiter, MAVEN. We have analysed Martian meteorites that have fallen to Earth. We have used Earth-based telescopes and space-based observatories to study the Martian atmosphere. We have spent tens of billions of dollars. We have invested generations of scientific careers. The motivation throughout has been twofold. First, scientific. Mars is the most accessible place beyond Earth where life might plausibly have existed. Second, almost romantic. If we find even a single fossilized microbe in the bedrock of an ancient Martian river delta, we will have answered, for the first time, a question that humanity has been asking for as long as there have been humans to ask it. Are we alone? The answer would be no. We are not alone. Life is not unique to Earth. The universe is biological. The discovery would be celebrated. It would be on the front page of every newspaper. It would be the lead story on every news broadcast. It would be the single most important moment in the history of biology since Darwin. It would change how every child in every classroom understands their place in the cosmos. And Bostrom argues, with what I think is unimpeachable logic, that it would be the worst news humanity has ever received. Here is why. Mars is right next door. Earth and Mars are essentially in the same neighbourhood, orbiting the same star, exposed to roughly the same population of asteroids and comets, irradiated by roughly the same solar wind, formed out of essentially the same primordial dust. They are not perfect twins. Mars is smaller, drier, colder, and has a thinner atmosphere. But cosmically speaking, Earth and Mars are sitting at the same table. If life emerged independently on both Earth and Mars, that is, if Martian life arose from local chemistry, not from a meteor that carried Earth life there or vice versa, but truly independently, then the inference is direct and unavoidable. Two independent origins of life on two adjacent planets in the same star system means that abiogenesis is a process that happens reliably given the right conditions. It is not rare. It is not the once-in-a-galaxy event that the rare Earth hypothesis hoped for. It is just chemistry. Stir the pot long enough, and life emerges. If life emerges reliably whenever the chemistry is favourable, then the universe is biological. The Milky Way contains billions of habitable worlds. The fraction of those worlds with at least simple life is essentially one. Life is not the bottleneck. If life is not the bottleneck, then the great filter is not at the origin of life. The filter is somewhere else in the sequence. And the question is, where? If we find Martian life that is similar in complexity to Earth's earliest life, simple bacteria, archaea, then the filter could still be at the eukaryotic transition. It could still be in the long climb from prokaryotes to complex cells, the climb that Lane and Martin identified as the single most improbable step in all of biology. We would still have a plausible behind-us filter to hide behind. The graveyard would still be in the early going, not on the road ahead. But if we find Martian life that has reached even slightly higher complexity, eukaryote-like cells, multicellular structures, recognizable biological tissue, then the eukaryotic transition is not the filter either. The filter would have to be later. It would have to be in the transition from complex life to intelligence, or from intelligence to civilization, or from civilization to interstellar survival. The filter would have moved further down the chain, closer to where we are, and if we ever find evidence of complex multicellular Martian life, coral-like structures in ancient Martian seas, fossilized impressions of soft-bodied organisms in mudstone, anything that would not look out of place in Earth's Precambrian rocks, then the filter would have to be after multicellular life. It would have to be in intelligence or in technology or in long-term technological survival. It would be standing somewhere very, very close to our present. The closer the filter sits to where we are, the harder it is going to be for us to pass through. The most complex Martian life we find, the worse the news. Bostrom's clearest statement of this point is that, paradoxically, the best possible news for humanity's long-term survival would be to find Mars sterile and to find every other world we ever investigate sterile. A universe in which life is extraordinarily rare is a universe in which the filter is at the start, behind us, already past. A universe in which life is abundant is a universe in which something far more dangerous is ahead. You can already see, in the slow trickle of evidence over the last 20 years, what this argument is going to look like when the data actually arrive. The Curiosity rover, in 2014, detected methane in the Martian atmosphere, a gas that, on Earth, is produced primarily by biology. The detection has been confirmed by subsequent observations. The source is not yet known. The Perseverance rover, currently operating in Jezero Crater, is caching samples for a future Mars sample return mission that, depending on which year you ask, will or will not be funded by Congress or the European Space Agency. The samples include sediments from an ancient river delta that 3.5 billion years ago would have looked very much like the kind of environment in which Earth's earliest life is thought to have emerged. Now imagine standing in Jezero Crater on Mars, beside an open trench dug by an automated rover. The Martian sun is small and pale. The sky is butterscotch. At the bottom of the trench, in a layer of mudstone 3.5 billion years old, the rover's spectrometer has found the molecular fingerprint of something that almost certainly was once alive. A microbe. A simple one. Dead for billions of years. You're looking at the second independent origin of life ever confirmed. You stand there in the cold, thin air. The discovery is the largest in the history of human biology. The press conferences are being prepared. The scientific papers are being written. And in that same moment you understand exactly what it means. The great filter is not behind us. The thing that kills civilizations is something we have not yet hit. It is something close. Closer than Mars is to Earth. This is the inversion that gives Bostrom's argument its full weight. The discovery we've been hoping for, the discovery we've been pouring billions of dollars and decades of scientific careers into pursuing, would be the discovery that tells us that whatever has stopped the galaxy from filling for 13 billion years is something that is going to stop us too, within the next few centuries. We have not yet found Martian life. The samples have not yet been returned. The rover has not yet drilled into the right rock at the right moment. The question is still open. But the experiment is running, and the next 20 years are going to bring an answer. The answer might be no. Mars is sterile. The filter is behind us. Breathe out. The answer might be yes. Mars carries microbes. The filter is ahead. Hold your breath. The answer might be worse than yes. Mars carries the fossilized impressions of something complex. The filter is sitting on top of us, and the silence we hear from the stars is the silence of every civilization that ever stood where we are standing now. The math insists, one more time, the math says that the closer Martian life sits to Earth life in complexity, the closer the filter sits to our present in time. The math will not let us look away. Whatever the rover finds, the math will read its consequences out to us in numbers we cannot wish away. This is layer 1, the scariest single piece of the Fermi paradox. The realization that our greatest empirical hope is, structurally, the worst possible empirical outcome. The realization that, if we find what we have been looking for, we will have confirmed our own death sentence. There is a quieter version of the same point that is worth noticing before we close this layer. It is the version that does not depend on Mars. It says that, even without Mars, the structure of the great filter argument tells us something useful. The mere fact that the galaxy is silent, independent of anything we learn about Martian biology, already places a constraint on where the filter can be. Each new exoplanet that is found to lie in a habitable zone, each new atmosphere that is shown to contain water vapor, each new piece of evidence that the conditions for life are common, pushes the filter further along the chain. We do not need to find a Martian microbe to suspect that the filter is ahead. We just need to keep finding evidence that the chemistry of life is universal. We have been finding that evidence steadily for 30 years. The implication is the same as Bostrom's, just on a slower timeline. The more universal the chemistry, the more local the filter must be. This is why every JWST observation of an exoplanet atmosphere is, in a structural sense, related to the Fermi paradox. Every detection of organic chemistry in a forming planetary system is a vote about where the filter sits. The data points have been accumulating, all of them in the same direction, for as long as we have been gathering them. They all point toward a universe in which the chemistry is easy and something else is hard. The data has not yet told us what the hard thing is. The data may take centuries to tell us. The data may never tell us, because we may not be around long enough to hear the answer. There is one more thing to say before we end. It is the meta-realization. It is the shape of the answer set as a whole. It is the part that, when you sit with it, makes the silence we have been listening to start to mean something very particular. Part 12. The shape of an answer. Let us pull back. We have walked through 10 layers of the paradox. Each layer has removed a comfort. Let us count them, one last time, before we close. Layer 10 was the math. The Drake equation, run with modern data, predicts a galaxy with more civilizations than zero. The math insists. Layer 9 was deep time. The Milky Way has been here for 13.6 billion years. Even at the slowest plausible colonization speeds, the galaxy has had time to fill many hundreds of times over before our solar system formed. Layer 8 was universal chemistry. The ingredients of life are not rare, they are galactic. The molecular building blocks of biology are the standard output of cosmic chemistry. Wherever there are warm worlds with liquid water, the kitchen is open. Layer 7 was the von Neumann argument. A single civilization, anywhere, ever, with a self-replicating probe, would have filled the galaxy. The fact that no probes are here means no such civilization has existed. Layer 6 was SETI. 65 years of listening with the best instruments humanity has ever built has produced precisely 0 confirmed extraterrestrial signals. The silence is not abstract. The silence is measured. Layer 5 was the zoo. The galaxy may be full and aware of us, but has chosen to remain silent. Under this reading, we are an exhibit and not a participant. We are watched. Layer 4 was the dark forest. The silence is enforced by every civilization choosing, rationally, not to broadcast. The galaxy is a battlefield in which speaking is dying. Layer 3 was the berserker. The silence is enforced not by mutual choice, but by automated weapons left running by an early paranoid civilization executing extinction protocols on any technology that becomes loud enough to be detected. Layer 2 was the great filter. Some step in the chain from non-life to galaxy-spanning civilization is nearly impassable. We have not yet determined which step it is. The candidates ahead of us look uncomfortably similar to the headlines of our daily news. Layer 1 was the Martian death sentence. The discovery we have been hoping for would confirm that the filter is not behind us. The filter would have to be ahead. The closer we look, the closer the filter sits. Now zoom out and look at the structure of the answer set itself. This is the third emotional anchor. It is the heaviest one. Every category of answer that survives scrutiny demands that humanity be in one of a very small number of positions. Look at the list. If we are early, if we are the first civilization in the Milky Way to make it this far, then we live in an unmarked territory with no precedent. There are no other survivors to learn from. There are no predecessors to mimic. The lessons of our long-term survival will have to be written by us, from scratch, without external assistance, on a timeline of our own. We will be, in that case, the precedent that some later civilization, billions of years from now, will study. If we are late, if the filter has already taken every civilization that ever existed and we are next on the list, then the galaxy is a graveyard, and we are walking through it without knowing where the bodies are buried. The reason the silence sounds the way it does is that everyone who ever could have spoken to us is dead. They were not killed by hostility. They were killed by the same thing that is, in this reading, coming for us. If we are watched, then we are a specimen. We are not in control of our own future. The criteria by which the watchers decide when to break their silence are unknown to us. We can do nothing to influence them. We are an exhibit, and the exhibit will end when the curators decide it ends. If we are hunted, then we are a target. We have been broadcasting our position for 125 years. The radiosphere is propagating outward at the speed of light. It cannot be recalled. Somewhere in that sphere, in this reading, hunters are doing their math. We do not know how long it will take for them to act. We do not know if they have already begun. If we are tolerated, then we are tolerated only until we stop being small. Eastivation predicts that mature civilizations have left guardian protocols in place to prevent their resources from being claimed by upstart species. The threshold of small is unknown to us. We are at the threshold now, or we are approaching it. We do not know which side of it we are on. The scariest single feature of the Fermi paradox is that, of these answers, the only ones we can act on are the dangerous ones. The filter ahead reading says we can try to identify our most plausible failure modes and reduce their probability. The dark forest reading says we can stop broadcasting. The berserker reading says the same. The estivation reading says we can try to stay small enough not to trigger the protocols. The zoo reading and the grabby aliens reading, the ones in which everything is fine and we're simply in a structurally normal position in cosmic history, happen to be the ones over which we have no influence at all. The actionable answers are all the dangerous ones. Survival, in every actionable scenario, requires us to behave very differently from how we currently behave. And yet broadcasting is essentially what we have done since the early 20th century. The 75-year-old radiosphere is the first thing about our civilization that could possibly be noticed at interstellar distance. It is also the easiest thing to interpret as either a greeting or a threat. We have, in effect, run an unrepeatable experiment whose outcome we cannot predict and cannot reverse. The signal is out. It is 125 light-years from Earth and growing every day. The Arecibo message of November 16, 1974, is now 100 light-years from Earth, propagating outward at the speed of light, addressed to no one in particular, signed by humanity as a whole. We have, as a species, written a letter to the galaxy. The galaxy will read it when the galaxy reads it. We will not be there to manage the reply. There is a quiet observation in some of the older literature on the Fermi paradox that I want to leave you with. It comes, in different forms, from Hart, from Tipler, from Bryn, from Hansen, from Bostrom, from many others. The observation is this: the silence we hear is not nothing. The silence we hear is data. It is the largest data set we have. It is the most consistent observation in all of astrobiology. We have been listening with increasing care for 2/3 of a century, and the cosmos has given us, for all our effort, exactly the same answer it gave Fermi over lunch at Los Alamos in 1950. Where is everybody? The question has been with us for 75 years now. It has driven the founding of an entire scientific field. It has produced shelves of books and stacks of peer-reviewed papers. It has spawned multiple billion-dollar listening programs. It has not, in all that time, produced an answer. But the silence we hear when we ask the question is itself an answer. We just do not yet know which sentence it is forming. We do not yet know whether the silence is the silence of a wilderness, or the silence of a graveyard, or the silence of a forest holding its breath, or the silence of a dormitory waiting for a colder universe, or the silence of an exhibit hall where the curators have agreed to leave us alone for a little while longer. The scariest truth is not any single answer to the Fermi paradox. The scariest truth is that every available answer requires us to be unrecognizable to ourselves in order to survive it. There is no door at the bottom of the staircase that leads back to the comfort of the room we were in when we started. The room is gone. The staircase has only one direction. We're going to keep looking. We're going to keep listening. We're going to keep building bigger telescopes and pointing them at more stars and recording more data and analysing it with better algorithms. Some night perhaps we will hear something. Some night perhaps the signal will repeat. Some night perhaps the answer will come and the silence will end. We will know which sentence it was forming. We will know whether we should have stayed quieter or louder, or whether nothing we did was ever going to matter. Until then, the question Fermi asked over lunch is the question we will keep asking back. The answer, whatever it turns out to be, is being delivered to us in the only language the universe has ever used to speak with us. It is being delivered in silence. We just have to keep listening, and keep being honest about what we hear, and keep being honest about what it might mean. Where is everybody? The math insists they should be there. The chemistry insists they should have started somewhere. The deep time insists they should have arrived here long ago. The probes are not in our asteroid belt. The signals are not in our antennas. The infrared waste heat is not coming from the nearby stars. The 72 seconds of the WOW signal in 1977 remains. After almost 5 decades of follow-up, the closest we have ever come to a fingerprint, and the silence on either side of it has never softened. We have looked, with the most patient instruments humanity has ever built, in every direction we know how to look. The cosmos has answered us in the only language it appears to use. The cosmos has answered us in silence. The silence is consistent. The silence is steady. The silence has been with us for as long as we have been listening, and there is no sign, anywhere, that the silence is about to break. That is the truth Fermi noticed at lunch in 1950. That is the truth the math handed him before the soup was finished. That is the truth that 75 years of careful science has, layer by layer, sharpened rather than dissolved. We did not invent the Fermi paradox, we discovered it. And what we have discovered, when we follow the logic all the way to the bottom of the staircase, is that every answer the universe has left available to us is in some structural sense a sentence we did not want to read. We will keep listening anyway. Because that is what we do. Because the question is too important to stop asking. Because the silence is still data, and the data is still being collected, and somewhere in the long, slow scan of the sky, there may yet be the beginning of a signal we have been missing. We will keep building the telescopes. We will keep pointing them at the stars. We will keep being honest about what we hear, and honest about what it might mean, and honest about the fact that, in 75 years of trying, the cosmos has not yet given us the answer that any of us were hoping to find. Where is everybody? The math insists they should be there. The silence is the answer.